Hey, in this video I'm going to describe how to do multivariable optimization. Single variable optimization is the process where we find local max and local min of a function using calculus. So we take the derivative, set the derivative to 0, solve for x. That gives us our set of critical points, at least for well-behaved functions. Then we need a method to diagnose whether those critical points correspond to max, min, or neither. So our choices were the first derivative test or the second derivative test. And we knew that a max corresponded to something that looked like the top of a hill, and the min corresponded to something that looked like the bottom of a valley. For multivariable functions, we have the same type of picture. A maximum looks like the top of a hill, like this. Minimum looks like the bottom of a valley, like this. There's more complex functions that have nicer, maybe not nicer, but more interesting pictures. I'll show you one right now. So this is a function involving trig functions, sine of x plus sine of y. We'll talk about trig later on. I've graphed this in Google, just using the command plot sine x, brackets around the x, plus sine y with brackets around the y. And what's nice about Google graphing is that you can rotate and visualize the graph this way. It's neat. It's kind of like a toy. You can't do much with it other than look at it. Can't really solve problems with it, but maybe you'll want to play around with it a bit. So we have this picture of what a max looks like and what a min looks like in 2D, and the picture translates very well to 3D. Without the picture, we can still define a max and we can still define a min in the following way. A maximum exists at the coordinate a comma b if the output of the function at a comma b is locally big. You can't get a higher z value or a higher height nearby. So if someone says that 5 comma 4 is the location of a global max, you go to 5 comma 4 and you look around, like look near your feet. What do you see? Do you see anything higher than that? Do you see a higher elevation? Any bumps? If you don't see any bumps, you're at the top of a hill. Now, if you see another hill 6 kilometers away and it's higher, doesn't matter. You're still standing at a local max. So that part of the definition stays with us. Local min, very similar way to define. You are at a local minimum at C comma D if when you're standing there and you look around near your feet, there's no lower elevation. But the value of the function at that point is smaller than the value of the function at nearby points. There might be a lower value somewhere else, doesn't matter. Local minima, there can be multiple local minima on a function, just like there can be multiple holes dug into the ground. We're not going to use graphs to find local max and local min for single variable or multivariable functions. It's quite the opposite. We might use information about local max and local min found algebraically to give us information about the graph. So finding these types of locations algebraically is the goal. And the way we're going to do this is we're first going to make a list of locations that could potentially have local max and local min. Those are the critical points, just like before. Then we're going to classify or diagnose those points as max, min, or neither. For one variable functions, we found critical points by setting the first derivative to 0. For two variable functions, we're going to set both first derivatives to 0, so the x derivative and the y derivative. We'll set them simultaneously equal to 0 and solve that as a system of coupled equations. Unlike linear systems of equations, so 3x plus 4y is equal to 8 and 2y minus 2x is equal to 7. Unlike those systems of equations which either correspond to two lines that intersect, at one point, two lines intersect at all points if they're the same line, or 2 points that don't intersect at all if they're parallel lines. Unlike that situation, which can have at most or that can have, let's say, one solution, 0 solutions, or no solution, a general system of nonlinear equations can have any bizarre combination of solutions. It can have exactly 2, or exactly 8 solutions. It can have exactly 3 solutions. It can have 0 solutions. So the process of solving this system is very interesting and often very challenging. So that's one of the things we'll have to spend time on inside this section. We'll get a list of candidate locations for max and min from this process for a given function. Then we'll have to classify them, to figure out like, what are they. If this was a first derivative test, we would take our critical points and plug them into the second derivative to see if the function is concave up or concave down. And then that would tell us if the critical point's a max or a min. For the second derivative, we will do something related. We'll plug our critical points into the second derivative, but before we do that, we have to do something else. So our full procedure is, first we find the critical points. That means take the x and y partial derivatives, set them both to 0 and solve that system. So I'll show you how to do that. Then we'll apply the second derivative test, which starts with a new type of function. It's called the capital D function, or diagnostic function. It's a function of 2 variables, and it's constructed through the second partial derivatives of the function that we're interested in. The second partial derivatives and second fxx and fyy derivatives of f of xy. It's given by the product of the double x with the double y derivative, so f double x times f double y minus the mixed partial fxy all squared. This function tells us about the twistiness, in a sense, of f of xy. When we plug the critical point into this diagnostic function, if what gets spit out is positive, then that means that our critical point could correspond to a max or to a min. Then we have to kind of classify between those. We can take either f double x or f double y and plug the critical point into there. Right? I think we're supposed to take f double x plus f double y. It's called the trace of the what's it called? The trace of the Hessian matrix. Like there's all like it can get more complicated if you want it to get more complicated, or just try to streamline things, simplify them. It turns out that if you just take f double x and plug the critical point into there, if f double x is positive at that critical point, it means the function is concave up there. Concave up is this shape, which is the shape of a function around where it has a local minimum. Now, super important, you can't go straight to the f double x. You have to first do the capital D function. You only check f double x if the capital D function at that critical point is positive. Okay. So, what happens if capital D is positive and f double x is negative? F double x being negative means the function's concave down. Concave down around a critical point is this type of a shape, which means there's going to be a local max there. So what's this capital D function doing? If capital D function isn't telling the difference between local max and local min, what is it doing? Well, it's actually filtering out a different type of point called a saddle point. It's testing, is this point this weird third thing that you've never heard of before, that you haven't seen before? That's all the capital D function is really doing. And it's an important task. A saddle point is something that does not exist in 1D functions. It exists in 2D functions and exists in higher dimension functions as well. Now there's positive numbers and there's negative numbers, and in between there's 0. This capital D function can fail. It's not perfect. If it spits out negatives, that's great. It means it's a saddle point. You don't need any further analysis. If it spits out positives, it could be a max or a min, and then you need to use the f double x derivative or the f double y derivative, your choice, to find the concavity. But if it spits out the number in between, if it spits out a 0 as the output, then that means that this test has failed. That this diagnostic function cannot tell us what's happening at that critical point that causes the diagnostic function to be 0. And for this course, we call it quits right there. We say, I have no information about that critical point. Nothing can be determined. A saddle point is a point on a curve where the function is simultaneously trying to be the max and the min. I'm not an artist, and I'm about to show you or to prove that I'm not an artist, to mathematically prove that I am not an artist. If this saddle was on a horse, this is what the horse would look like. A little bit like a turtle or a dinosaur, because that's the best I can do. That's my horse. So that's just my attempt to show you what the saddleness refers to. If you put the saddle on the horse, then this is about to get worse. Oh man, there's a foot of some type. There's a person sitting on it. The other foot's on the other side, like that. So there's the person sitting on the horse. Damn. All right. It's so horrible. I can't even stand to look at it. So that's what the saddle point is. And what do I mean when I say it's trying to be a max and a min at the same time? Well, if you think about this curve on this direction. Oh no, don't do that. On this direction. So you're going up and then back down the saddle. So where the legs would be dangling on the saddle. In that direction, it looks like a maximum, like a local max. But if you think about the saddle in this direction instead, going from the back of the horse to the front of the horse, instead of from the left leg to the right leg or right leg to left leg of the person riding the horse, that looks like a local minimum. So its maxness or minness really depends on the angle at which you look at this picture. So I'll show you what this looks like for the function x squared minus y squared, which is a function with pure twist. This is the saddle point in 3D, and if I rotate it along one axis, I can't unfortunately easily, or can I? Maybe I'm a liar. Can I do it? Oh no, it doesn't. It really doesn't like that. Anyways, there it looks like a local minimum. And if I rotate it around the other way, this way, in the interior of it, that looks like a local maximum. So it just depends on the angle at which you look at the thing. Is it a max or is it a min? So there's your saddle. It's trying to be a max and it's trying to be a min at that point in the middle of the saddle. And that's what the diagnostic function d is trying to filter out. It's trying to get rid of those types of critical points because they're not max and they're not min. They're kind of both. They're kind of weird. They're important. They're often an important part of the analysis, but if you're looking for max and min, you don't want these. You want to get rid of them and then focus on the other critical points. I'm not going to read this. You can read it on your own. This is not testable stuff. It's a little bit more of a geometric explanation for how the diagnostic function capital D of x, y works. It's essentially just describing the capital D function tells you how twisty the function is relative to how bulgy it is. So it's like a battle between the bulginess of the function given by f double x and f double y and the twistiness of the function given by fxy. If the fxy part is stronger, then that means it's really twisty. It's saddly at that point. I'm making up words. Twisty is a word. Saddly is not a word. Now, where does it come from? Mathematically, instead of geometric, well, geometrically is mathematically, but algebraically instead of geometrically. So it comes from what's the so-called determinant, and that word doesn't mean anything to you unless you took Math 1229 or Math 1600 or a different course in linear algebra. It comes from the determinant of something called the Hessian matrix. Hessian matrix is a 2x2 matrix composed of the second partial derivatives of the function with respect to x and y. We use the fact that the mixed partials are equal to each other, fxy is equal to fyx, to make that second term, the term that's being subtracted from the down product minus up product, to make that term just replaced by f of x, f of xy all squared. This is not testable either, but some people, especially those from Math 1229, like to see that there is some relation between the courses. What if you have three variables? What would your Hessian matrix look like? And what will the determinant look like? Anyway, back to Math 1230. So I just want to highlight something because I always get questions about stuff like this. Do you have to study this? No. Should you care about it? that depends on you. Only if you're interested. Don't pursue it otherwise. Same with this slide. You can look at this a little bit further if you're interested, and if you're not interested, you can forget about it. Okay, this stuff, now we're into stuff that everyone has to care about. Finding extreme values, a recipe. Our first step of the recipe is to take the first partial derivatives, the fx and the fy. We set them in the second step equal to 0 and solve. This is, generally speaking, the hardest part of the problem, is solving this system of equations. So if the whole question takes 3 pages for you to do, 2 pages will be step 2. And the rest of the problem is the rest of the writing. Then we find the second derivatives, the f double x, f double y, and the mixed derivative fxy. Step 4, we take the results from step 3 and we use them to construct the diagnostic function. Then step 5, we take our results from step 2, our critical points that we found by solving that system of equations, and we sub each critical point separately into the diagnostic function. Then, based on the diagnostic function's output, if the diagnostic function spits out something negative, we throw those away, they're saddle points. If it spits out something positive, then it means that they're max or min, and we have to use the second derivative test. So we plug the critical point into fxx and see if it's positive or negative. Then, if necessary, we don't always have to do step 7, only if needed, find the value of the function itself at that max or min. So what is the output? How high is the mountain at its max? What is the maximum? What is the profit of the company at its maximum profit? Like at the point that where it has maximum profit, what is that profit at that point? Some people love diagrams, like charts like this. And maybe this is something that you would draw when you're thinking about algorithms, about a method for doing something. You can draw diagrams like this for anything, not just math problems, but any type of procedure. How to make a cheese sandwich. That's what my kids had to do as a grade 4 lesson in programming, computer programming. Draw a diagram for how to make a cheese sandwich, and think about what the computer would do if you get something wrong. I don't know if you guys had ever had to do something like that. But anyways, our diagram for not making a cheese sandwich, but our diagram for finding where the max and min are for multivariable functions is this. You start with your function, you take your fx and your fy, and then you use them to find the critical points in the middle there, in the middle in the green at the top. You also use them to find the ingredients you need for the capital D function. Then you take your critical points and plug them into the capital D function and do your interpretation. So there's different layers and different stages, and different parts of your process are used in multiple spots, used in multiple ways. So I'll show you how this process works from beginning to end, but I think it's good to break here and make a separation between the theory and the applications.